digital twins and wind-assisted propulsion systems. And I'd like to say a couple of things before I hand over to the moderator. So firstly, thank you to the Netherlands Maritime Technology for hosting this, and to Joshua Lacey and Frederik Gerhardt, our two experts in this field, for joining us on the panel. And I'm going to be handing over to Craig in a moment, but before I do, I'll just mention about the question and answers. If you could put any questions in the chat format, or raise your hand electronically with a little yellow hand. You can try and get Craig's attention as well by waving frantically at him as well, if that's possible. And of course, this is going to be recorded, or it is being recorded. So please just be aware of that. So without further ado, I'm going to hand this over to Craig Eason, who is the editor-in-chief of Fathom, and a very good moderator for these types of events. So Craig, handing over to you, and I'll see you at the other side.
Good, thank you very much, Gavin, and good morning to everybody. Welcome to another one of these WASP webinars, where the objective is to sort of encourage learning and understanding around the whole development of these technologies. And the idea here is to bring a little bit more understanding about how the concept of digital twin can be applied within the scope of the WASP program, but also into wind propulsion in general. We've heard a lot about, everybody probably has heard a lot about digitalization and digital twins in particular. So what we thought we would do is look at what a digital twin is. We asked a question, we sent a questionnaire, a couple of questions when people registered, and we noticed that some people had a little bit of understanding about what a digital twin is. I think of all the people who are listening, probably a third to a half know a little bit about digital twins but want to know more. A small percentage are working in the digital twin sphere, so possibly want to understand how it can be applied to wind assist or wind propulsion now and in the future. And others just had no understanding at all and just want to learn a lot about this. So what we thought we would do is we've asked Frederik Gerhardt from SSPA to give a sort of introduction to what digital twin is and how he sees it being applied. And then we'll go into more details with Joshua Lacey as well to see how this is being applied within the WASP webinar. Like Gavin said, it's as much about you asking your questions as me. So we're going to get Frederik and Joshua to do their short presentations initially, so that'll take about 15 to 20 minutes. I'll start the questions rolling by just having a conversation with them and getting a discussion going. But please, you're more than welcome to put your comments and questions in the chat function on Zoom. I'll be able to look at them and ask them as they fit into the conversation. Or as Gavin mentioned, just raise that little electronic hand and start waving at me like mad. I'm looking at everybody as I speak, so I can hopefully see you, but try and get my attention. You're more than welcome to open your microphones to ask the questions, but as you probably understand, after about 2 years of probably complete digital overload here, keep your microphones muted. I don't want to hear you coughing and drinking your cups of tea and typing away on your keyboards while we listen to Joshua and Frederik. So that's it for me for the moment. So I'm going to hand over now to Frederik. He's going to share his screen and give a short introduction for us. So Frederik Gerhardt from SSPA in Sweden, please, the digital floor is yours.
Well, thanks very much. So as you just said, I will give a short introduction into the concept of digital twins. And I will share my screen. You should be able to see a full screen presentation now. Is that right?
We can.
Yeah.
Yep.
All right. Okay. Good. All right. So yeah, as we've just heard, many of you answered during registration that they've heard about the buzzword digital twin and that they want to learn more about it. So that's really the purpose of my presentation today, to just give you a bit more background on digital twins, what they are, in what context they can be useful, and also how they can be applied to wind ships. This concept of a digital twin is nothing new. It was developed during the 60s as part of the Apollo space missions. But today the word is more associated with the fourth industrial revolution. And with this, I mean the advent of integrated cyber physical systems, a development that has started maybe, I don't know, 15, 20 years ago. And in the circle on the right hand side here, you've got some of the technologies that are part of this industry 4.0, as it's called. And the digital twin concept can be somewhere placed in between maybe system integration, simulation, and big data. But what exactly is a digital twin, and what are its characteristic features? In this slide here, I've illustrated one of the key features of a digital twin, namely that a digital twin is a digital representation of something real, of a physical asset or a piece of machinery, or in our case, a ship, simply. And now the real object, there's a white cube, and the digital representation exchange data. And depending on whether this data flow is manual or automatic, these are dashed or solid lines, you call the pair differently. On the left-hand side, you've got this the classical modeling approach that most of us know about, where sort of the data flow in both directions is manual. And then in the middle, you've got something called a digital shadow, where there's a physical object feeds data to the digital counterpart automatically, but decisions are still made manually. Sort of the other data flow, the other directions is manual. And then on the right, finally, you've got the real digital twin, where the data flow is fully automated and probably happens in real time or near real time. So this is one feature of a digital twin. But there's another feature that is typical for a digital twin, and that is that the digital representation usually looks at multiple aspects of the real object. And I've tried to illustrate this here using different layers in this blue cube. So you might have one layer or a sub model really looking at ship performance. Another one considering operational aspects, a third to model economic considerations, and and so on and so on. So in combination, this is more than just a CAD model of a ship or CFD simulation that looks at flow physics. It gives you a picture of the whole of the whole asset. There's a physical ship in our case. Now on the other side of the white cube, you obviously have the real ship, which is equipped with sensors and gauges that measure certain properties, and now feed those back to the digital twin, probably in real time usually. And a final note on this slide: the sub models behind the different layers in the blue cube in the digital representation, they can be physics based, but they could also be based on machine learning or a combination of both. So there's a sort of number of techniques to choose from. And another feature of a digital twin is that they usually grow over time, from an embryo into something that's viable. So in this slide, I've tried to illustrate this for the case of a wind ship. If this is a timeline of the shipbuilding process, from making the business case over design and building phases to finally operating the ship, then you obviously start with an idea and you end up with really like a physical ship in operation. And from our perspective at SSPA, the digital representation of this physical ship quite naturally grows during this process. So in the beginning, when making the business case, you might have a relatively simple digital model, maybe with just two layers that model, say, performance and economics. But over time, the layers get more complex in itself. So the models behind them get more complex. And you might start to add layers to the digital twin. So at the beginning, well, you go from finance and performance. You might add operational aspects and risk aspects to your models, and this thing just grows over time, both in number of layers and in sort of complexity, power of the models behind the layers. And when we come to the question how you model all those things, in the beginning, you will probably use a lot of physics-based modeling approaches, while at the later stages, once you sort of have done seed trials and start operating the ship, you could probably also use machine learning approaches. Yeah, so this is sort of a timeline of how a digital twin can grow from sort of something very small, from an embryo, into something that's a bit bigger and more useful. So much for digital twins in general, but what do you do with them, and how can they help you? And then the last two slides that I have, I will give you an example of what I think is a useful application of this digital twin approach. This here is the Buckow, Flanders first rotor ship, and this was operated in the sort of manner that's illustrated in those pictures. So you had like an experienced captain on an open bridge, an engine, order telegraph, and you had those two little wheels here, which were used to control the rotor RPM. And well, if you think about such a setup, then arrival times in port and fuel savings are obviously a direct result of how good this captain is in juggling rotor and propeller RPM. So the question is, can we do better? And I've illustrated this in the next slide. This, by the way, on the left is Anton Flettner himself. So 100 years on, how can we do better? And how can a digital twin maybe help us with operational questions? Here I've listed a few questions which I think a digital twin can help to answer. It's the question of arrival time, emissions, fuel savings, and so on, which we've seen in the last slide was done in the brain of a captain. But using a digital twin, we can actually model those things and make decisions in real time. So we could, for example, if you look at the series of the three blue plots here, we could make a prediction depending on how many percent we're sailing, how much of our propulsive power comes from the sail, what happens to our estimated time of arrival, which usually would go up if you increase the percentage of sailing. What happens to our time charter equivalent, to, well, let's say the profit you get out of the ship each day? Will it drop down as you increase the percentage of sailing, which it usually does because you would be going slower, or might it go up if the fuel price is high enough, if there's emission trading schemes and all those things? You might end up in a situation where time charter equivalent actually increases with the percentage of sailing. And obviously our emissions in CO2 emissions in gram per ton mile, they will go down with percentage of sailing. So yeah, a digital twin can help you to sort of plot all those figures and make decisions on the bridge. Whether you want to increase propeller RPM or not. And the last plot here, CII, CO2 emissions. There's also a long-term aspect to this, you will get like an annual budget for your CO2 emissions. And if you're over, your ship might be derated next year. So if in January I've used so and so many percent of this budget, what's the most likely scenario? What will happen over the rest of the year if I increase my power levels, my fuel consumption? So it's those kind of questions that I think a digital twin can help to answer in ship operations. And this was my short introduction to digital twins in sailing. I don't know, Craig, do we want to take
that's great. No, I'll
questions
take some,
now, or
I'll take some questions after. We'll go through.
Okay.
But I've just got one more sort of generic question about digital twin here, just to sort of whet people's appetite and think about this a little bit, because when you're talking about digital twin, then I've always seen the digital twin as something that begins life ashore, so to speak, as the vessel design and the criteria for a vessel. I mean, I'm taking a broader picture here, not just the on a WASP angle. It will start with a digital design. It will go through the CFD, the CAD environment. It will go through the testing, etc. So to an extent, the real vessel is a copy of the digital vessel. When we talk about digital twins, we think about twins, but I've always seen the real ship as being the real ship and the digital being the copy, if you like. But really what you're saying here is the digital starts first and the copy to an extent is the real ship.
Yeah, well, this is how I would see it, because if we jump back into this slide, it's really like when someone makes a business case and say, is there any point of putting a wing sail on this particular ship? We start building a model. It's not very complex and it might not have very many layers, but it's a first embryo. It's not coupled to as a real ship, because there is no real ship yet. So I mean, from the sort of building stage, and you could talk about there's a pair of, well, digital twins, but it's I think it starts earlier. It's sort of grows naturally during this process.
One of the angles I want to then come on to later, after we've heard from Josh, is how we apply this thinking when a lot of the wind assist solutions that I've seen going onto vessels are largely retrofits. So how does that discussion then fit into the retrofit picture as well? But we'll move on to that, I think, after we've heard from Josh. So Josh, if I could ask you to take over now, please. Frederik, if you can stop sharing your screen, then we can let Josh share his screen. And just a reminder to everybody, after we've heard from Josh, I'll start the questions, but please put your questions into the chat or raise your hand and get yourself involved. Keep yourselves on mute until then, but then you're more than welcome to unmute yourself and take part in a discussion. We've got a good hour on us, and we've got 30 people on this call, so I'm sure all of you have got lots of questions. I hope you're here to ask questions and get your questions answered. Anyway, so Josh, over to you, please.
Can you just take over the screen? I've lost the control bar.
I think I can. So I think now
there you go. I've seen
everyone
it.
should be seeing my screen. Okay.
Yeah.
If you could just make it a bit larger, please, Joshua.
Is it full screen now?
No,
hopefully.
Now it is. Now it is.
Now it is. Okay, excellent. And maybe I'll put on my laser pointer because sometimes that's useful. Okay, so yep, thanks Craig for the introduction, and thanks to Frederik for really a very nice introduction to what the digital twin is and really how it can be visualized, if we can say that, in a virtual sense, but also its application in an industrial context. So Frederik gave really a very nice overview, and I would say my presentation is a direct continuation of that, and maybe a very specific use during the WASP project. And as Craig mentioned, obviously WASP is dealing with all ships that are retrofitting wind propulsion units. So these are not new ship designs, new ship builds. These are existing ship builds. But that being said, the digital twin and the process, it's still quite relevant. And I would say overall, there's the overarching theme, which which drove the point home very well, is that there's this continuous feedback loop, right? The cycle of we take information, data, from experiments and trials from the real world, from the physical asset, which gets fed into the digital twin model to continue to develop it and its complexity and what sorts of effects it can capture. And then of course, those results are fed right back into the design or the improvement of some operational aspect of the physical asset. So having that feedback loop between the two is really the key component of the digital twin concept. So I'll say, so where do we start and then where do we end up? So where do we start? Well, ultimately we start with a very general framework. You know, digital twin is, I think Frederik did again a very nice job to sort of demystify what it is. It's a model-based approach to simulation. So at its core, at least our approach within the WASP project has been to start with a very generic framework for a cargo vessel. And so that is start with some simple governing equations that apply to just any general vessel, and then take this framework and of course adapt it to our specific use cases and the specific applications, which in this case are each one of our ship owners and they're the different ship configurations that are involved in the project. And we actually have quite a number because we have 5 different ship owners, all of whom have different propulsion configurations, but also who have a range of wind propulsion technologies. And so you can't just simply take that base framework and apply it to any ship, right? Again, you need the direct feedback from the specific use case or the specific application to go into the digital twin to then build up those layers so that you can capture more effects and you can say something meaningful about the operations of those ships and hopefully the improvement of their operations or about future design in the case of these retrofit applications. So this is just a brief look at, if you could, you know, the digital twin, of course, it exists just on a computer and code. It's a simulation. If I could give any kind of visualization, I would say, okay, we start again with this just kind of basic idea. What's our reference frame for the ships? What's the basic layout? What does it look like? Where are the wing sails? Where are they in with respect to the hydrodynamic center of gravity? This kind of thing. So it's not necessarily something that's, of course, embedded in the code itself, but we can visualize it at least as a start for us to do the development. Now, specific to wind, because of course that's one of the main ideas we're talking about. How do we incorporate that into the basic framework? So on this slide, with the exception of the wing sail units here, it's really just for any general cargo ship, you know, without wind propulsion. Obviously, once we start to add wind propulsion units, we have to modify the governing equations that characterize the dynamics of the ship and how it operates when it's at sea and when these wind propulsion units are deployed. And so there's a few things that we need to consider. So first of all, we need to understand what the wind propulsion unit does at any particular wind condition. And that's, again, a big part of the digital twin concept, is being able to model or basically characterize the performance of all of these different subsystems within the vessel. You can take a very detailed approach, which would be to do a full CFD of the wind propulsion unit to try and characterize its performance at different conditions. But that process is obviously rather time consuming, and CFD is very difficult to do if you're trying to perform an optimization. So as Frederik mentioned, the idea is to have this feedback between the two in real time or something nearer to real time, so that you can actually say, okay, we're operating with some particular control strategy, but we could be doing better. How can we adjust? So CFD is not a real time solution. That's an offline simulation tool that we can use for a deeper understanding of performance. But so in the context of this project, we use basically performance data for each one of the wind propulsion technologies, which looks, for those of you, I'm sure many of you are very familiar with sailing and polar plots. We have essentially the performance data for the wind propulsion units, which tells us at any given particular wind speed, wind direction relative to the ship, we know what we expect the wind propulsion unit to be able to do in terms of the propulsive thrust that it's able to provide. So that's one aspect of which goes into the digital twin, is what is it actually able to provide in terms of thrust? And then the other aspect is, what impact does the wind propulsion unit have on the dynamics of the ship? And that's where we dive into the equations of dynamics, which I'm not going to go into a lot of detail, but what we've done for this particular application is it's a 4 degree of freedom model. And in each one of these dynamics equations, we have some additional term, right, which is a consequence of having that retrofit wind propulsion unit. And that, again, that is exactly what is encompassed by that term. Well, that is application specific to some extent. The generic framework is true for any of our ship applications, but obviously, again, the technologies are slightly different from one ship to another. The sizes are different, the way they operate is different. And so each one of those has some different consequences for ship operation. So that's how we include wind propulsion in this whole picture. And then if we step back even a bit further, right, to look at sort of the digital twin from a high level, well, then we get to the stage where we have all of the layers put together, right? So we have this dynamical model of the ship, sort of the hydrodynamic perspective of how the ship is traveling in water, what the hull resistance is, etc. We incorporate the impacts, if any, from the rudder, obviously the connection of the propeller to the main propulsion system, what sorts of losses occur there, also what sorts of control may occur. In this particular application I'm showing here, this particular ship has a propeller with variable pitch. So how that may come into play when we're using a wind propulsion unit, that's included in the model. Obviously the wind propulsion unit itself comes into the digital twin, and this capability, again, to control that actuate the controller for the propeller. So all of these different subcomponents, we have technical specifications from the ship owner, from the technology providers, and all of this, along with those generic dynamical equations, right, which are just a physics-based model, all come into the digital twin to eventually provide this overall, again, high-level view of ship performance, which then ideally we can use to assess how well the ship performs with the wind propulsion units. This is just some example from a recent conference paper. This I should mention because, of course, he's on the call, but I should mention it anyways. Is some very nice work that's been done by my PhD student. And so again, once we have the digital twin validated from using data, real world data from sea trials or experiments at the industrial scale, and we have all of the technical specifications, so we have the specific digital twin built that represents the physical asset, then we can start to, again, gain the deeper insight, and we can start to feed back into the physical asset to say, if we're at this condition, perhaps we want to adjust the propeller pitch based on this amount of wind thrust that's available, or maybe we want to downspeed or depower the engine, something to that effect. That's the idea, is really being able to feed back in real time or near real time a control strategy to try and improve operation and performance. That's in the sense of this retrofit solution. And then, of course, if you think to the design of a new vessel, well, then it's really how, building from the ground up of, okay, how can we incorporate the wind propulsion unit directly into the main propulsion system, and what's the interaction of the main engine, the propeller, possibly any other advanced propulsion components, if it's a electrified case, partially battery electric ship, and how do we incorporate that into the full picture of the integrated propulsion system. So again, I would just highlight the fact that the key of the digital twin concept is the continuous feedback loop between physical asset and digital twin, and the two really feed into one another, from the physical asset giving us real world data at the industrial scale for the specific application, which allows us to build up the complexity of what the digital twin can capture, which then, again, once we capture interesting effects, how to improve performance and operations of the vessel, we can feed directly back to the bridge or feed directly back to the relevant personnel that can hopefully take action on that information. So that's the end of my presentation. Obviously, the floor, I think, is open to questions. Craig, I guess you want to
Yeah,
take over from here.
Yeah, thanks, Josh. As I said before, everybody's welcome to pitch in with questions and comments and thoughts here. I know some of the audience have been working with digital twins, so perhaps they can give us some of their experiences with it as well. And the people who filled in the questionnaire saying that they wanted to understand a little bit more and learn what it's about, maybe they've got further questions as well. So as I said, put the questions and comments into the chat, or just say you want to talk, or raise your hand digitally or physically. It doesn't really matter. But let me start, and so to get the ball rolling, and just to raise a couple of points here, Josh, with you now. When you're talking about this learning from the onboard performance of the vessels that you've got within the WASP project, do you envisage the digital twin then to be allowing for improvements on the ship, or are we talking here about the digital twin being ashore and then that feedback? And it kind of goes a little bit into what Frederik was saying, because I was curious about the operational aspect of this, because I'd perceive digital twins to be quite intensive programs with a lot of different layers, as Frederik said. So does the digital twin itself sit ashore, so to speak, and parts of it sit on the vessel in some sort of form, or does it all sit on the vessel? What can you tell me about where the digital twin, if I can visualize it being somewhere, it kind of sits into that equation?
Yeah, no, that's a very good point. And I can say up to this point, yes, these digital twins within the WASP project are sitting on shore, right? And then we're taking results from the ships at sea, and again, building the layers. But that's not to say that something couldn't be implemented again in closer to real time on the ship. As these propulsion systems become more complicated, the example Frederik gave, right, with the original ship with Flettner rotors, okay, which is completely open loop manual control. Well, that's just, I mean, we could do such a thing, of course, but that's really not feasible for truly optimal performance, right? We have to have automatic control systems, or really a dedicated energy management system on these ships to realize optimal performance. So that's some of the idea with the digital twin. While it might originate or sort of start as the embryo on shore and be developed from these physics-based models, some of which may, and at least initially, be very detailed because we need that insight initially. But then as you move more towards the application at sea, you can move to things that are a bit more lightweight. Again, the example of, you can't do a full CFD of a wing sail or a turbo sail in real time to feed back into some energy management system. That's just not possible because it's too slow. But if you have what's essentially a lookup table to say, at this wind speed and this wind angle, this condition, this is what the sail should do, and this is where it should be pointed. That is something that you can build into a real-time control system. So yeah, you could almost think of the evolution of the digital twin too is moving as the layers build up. Some of those, while there may be more layers, some of those layers are becoming more lightweight, and then it's migrating from onshore to within an energy management system or control strategy on a ship.
Frederik, have you got any thoughts on that as well, in terms of where the digital twin sort of sits, and particularly in context of that layering you were talking about?
I totally agree with what Josh has said, and as you pointed out, the some of the layers might get more lightweight in terms of how they're modeled, and once a ship is in operation, instead of the CFD or even the lookup table, you could also start to collect historical data and then start to take a sort of machine learning approach, that you say, under those conditions, wind direction so and so, I've used so and so many tons of fuel per hour last year. Am I better now or not? And what were last year's settings, that you start sort of building up an operational sort of historical database.
I've just got on that sort of a similar theme here. I've got a question coming in from Giovanni Bailardi relating to this, and they said that, is the data I mean, I'll go into the data for the, he's got a question about the publicly available, how the data is going to be publicly available. But I just wanted to go on to his last point, his last question here of 3 questions. Is a ship full of sensors needed to perform the optimum control strategy? So in context of where we see the wind assist system sitting on a vessel, to get the most out of it, do we need a fully digital ship and a full digital twin to get that optimized response to the technology? Frederik.
Well, I think this the last question with sensors is really crucial to this digital twin approach, because you need to measure the state of your physical system in order to assess it and feed it back. So if you want to optimize rotor RPMs or sheeting angles or whatever, you need to know what, for example, the wind speed is and what the wind direction is, so that you can go, say, into your lookup table or whatever model you're using. So you know need to know what's happening outside. So I think this to me, this question is crucial, and it's not easy to do. I mean, wind speed measurements or just wind angle measurements, they're tricky on a moving ship. You get disturbance from the superstructure and so on. So I think there's a lot of room for research here.
Joshua, have you any thoughts on that?
Yeah, I mean, full of sensors, I would say, because of course you can really the sky's the limit in terms of how much you want to instrument the ship. So yeah, what I would say is there will be probably some initial phase, again, if it's a new design or it's some new concept where you may use a more extensive suite of sensors, but then ultimately the end solution is some stripped down set of sensors that is sufficient enough, right, to give you the information that you need for feedback to actuators. So actuating a sail, actuating the pitch of a propeller, actuating an engine, whatever it may be. I mean, a good example is, I know on one of our partnerships, initially they had a full LiDAR system installed, and that was actually to investigate the wind around a Flettner rotor. Now, the end solution was not to use a LiDAR on the ship, because that wasn't necessary at the conclusion, right? Once they had established the data set that they needed, essentially they were trying to decide where was the optimal place to put a sensor, a wind sensor. And that was determined from that more detailed experiment. But in the end, they didn't need a full LiDAR system. Would that be nice? Okay, yes, it gives you a full picture of everything that's going on and how the wind is affected as it comes over the hull. But is it absolutely necessary? Well, no, and probably also, frankly, not very practical.
And how would also, in taking that sort of one step further, when you're talking about all of the sensors and gauges that might be needed, when I have seen ships, when I've been working on ships, I'm full aware that the weather conditions determine how the vessel performs in the sea, particularly the wave and swell conditions that you might get. And that also includes slamming and other sort of forceful impacts on the ship. So when we're talking about data from the weather, what about getting the data from that kind of impact force on the vessel and how that translates to a digital twin scenario, and also for a digital twin scenario for a wind assist solution here? Because we talk quite often about getting continual data, but the slamming and the physical impacts on a ship like that, which could have damaging implications. How does that feed into the digital twin context here, Josh?
Yeah, so yeah, waves are challenging because I mean, at the moment we have a very simple model just to incorporate waves. So at least we have the capacity to include those effects on the dynamics of the ship. But yeah, for extreme or really adverse conditions, I mean, I would say, of course, it would be very useful to have that data collected, and that is not straightforward to get that, right? To get what is that physical force of the waves on the hull or the superstructure of the vessel, and the impact it has on the operation and the safety of the ship, and what impact indeed that may have on the propulsion unit. It's something I would say we don't currently, we're not accounting for, again, because it's something that's not necessarily so straightforward, but I can definitely say going forwards, probably having at least some information about adverse operations and adverse conditions will be necessary, because there'll be times when, yeah, of course the wind is favorable because you're in very high wind conditions, but that doesn't mean you can say, you have to, basically disengage or put the wind propulsion units down, because it's not safe, because they can either be damaged or again, it's just not safe for operation of the ship. So that is, I'll say, for full disclosure, I don't think that's something that we will answer in the context of this WASP project, and it's not necessarily the goal, but going forwards, we of course will have to, especially as the wind becomes a larger percent of the total propulsive force. And then the way that the ship is characterized in a regulatory sense starts to change. And that's also another very important aspect of this work and the understanding.
And Frederik, I mean, I don't know whether you want to comment on that, on the sort of the abilities of a digital twin to help with that slamming and other physical.
Yes, I can comment on this. It's I mean, as it is obviously to very challenging to model this explicitly and sort of on a physics-based model. But I think what you can do is you find out what the limiting conditions for your ship are, sort of. And now it's a kind of captain experience again. You say, okay, waves so and so high are critical. And from the wind propulsion system manufacturer that the maximum forces, maximum wind speed for the system are so and so much. So you start setting up what we call a sort of a risk layer to this digital twin. And you say, if I'm outside of my sort of safe operational envelope, I need to do something. I need to reef or change course or turn off the rotors, or just simply do something. And the digital twin, of course, can give you feedback on this. We've been considering giving feedback on really on rotor forces, kind of as a display on the bridge. That you see, I'm about 10% away from braking limit of my rotor, so it's getting towards a sort of dangerous situation. Those kind of things, which that's relatively simple to do. But then it's based on a more generic approach in the background. It's not sort of doing this in real time and really calculating forces in this particular instance. It's just sort of averaging and
Wonderful. Just a reminder to everybody, we've got another 45 minutes maximum here. There are about 27 people who want to know a lot more about digital twin and wind propulsion. So put your questions into the chat or raise your hand, and you can open your microphone or put on your webcam as well and talk to us. You're more than welcome. We're here for you to get your questions out as much as to listen to me and Frederik and Josh have a nice little chat for the next 45 minutes. But let me take, while I'm waiting to see all of those questions come flooding in, let me take another angle here. I'll start with Frederik, because when you're looking at that, I want to go back to that idea about starting the digital twin before you start building the vessel to some extent, where the digital twin comes first. I've seen some designs, these are not in the WASP project, because this is all retrofitting, but in the context of how we see some of these ship designs evolving, and then they go through CFD and they perhaps go through a model tank like we see behind you now and whatever. How does digital twin feed into that assumptions or those decisions about the engine capacity that might still be needed? Because clearly the whole conversation, the bigger picture here we got about the reason for wind assist propulsion is to reduce emissions and to reduce the development or reduce the reliance, of today's engines. So how does a digital twin fit into, I can understand here's a vessel, it doesn't need as much power, therefore it emits, uses less fuel and emits less emissions. But how do you use the digital twin in getting that balance because there are some designs out there at the moment that, are, very high on the wind propulsion, very low on the assumptions about the propulsion power, still maintaining sort of minimum safety limits. But what can you say about that ability to make that balance? So you push the envelope, so to speak, on the wind propulsion percentage.
Yes, I mean, at this stage, I wouldn't really call it a digital twin in the sort of very strong definition of the word, because there might not be a physical ship yet, or it's what you do is to find this balance. It's a sort of simulation approach. You look at those equations that Josh showed, and you try to find resistance curves for the ship, how much force is required to bring it up to a certain speed, and then you just need to make the decision, where does this force come from? Do I want to have it from the main engine? Should it come from the sails? And sort of what really is my goal? Do I want to have a sail assisted ship which saves 10-20%, or do I want to go all the way to 90% fuel reduction? And you can make those decisions, based on sort of a numerical simulation, and depending on what you do when it's a new ship, you will have to sort of do it all numerically, do predictions of the resistance curves. If it's a retrofit, you might have full scale data. Almost certainly you will have model test data. So it's simply a question of finding your best source of data there, and implementing this in a sort of performance prediction model.
Let me take that also and put now sort of the flip side of that, Josh, within the actual WASP project as well. And this comes back to the other question that Giovanni was asking in terms of the real versus the digital data, how they compared and validated. As a seafarer, I knew that I had on my ship, I had a chronometer. The chronometer was basically 3 clocks. The reason there were 3 clocks is because if you had only 2, you wouldn't know which one had gone wrong if it started to go fast or slow. You needed 3. So when you come to check the real versus the digital data that you were talking about, so it's a bit of sort of like validating the digital twin hypothesis in some respect. How do you compare and validate the data, and how do you then move forward to improve one or the other?
Yeah, I mean, as with any numerical simulation tool, of course, validation is key. Without it, the tool can give you any answer you want. So, in the context of the WASP project, we've conducted these sea trials, and actually the exact measurements that we get from one ship to another vary a bit, but there are some common measurements, of course. So for us, one of the main criteria to validate on is that we, in the digital twin, that we are able to reproduce the power demand of the vessel, of the real vessel. So at some particular speed, it obviously has some power demand, and that's something that we can reproduce in the digital twin, because ultimately we should be able to take in the demand profile of the ship, right? Which that's just a different way of saying what does the journey look like, the voyage, right? What is the power demanded for each condition at every point on the journey? And that's something that we should be able to absolutely reproduce in the model, because that's where we have to start to say, okay, how much of that propulsive force is going to then come from the wind propulsion unit, and how much is going to come from the rest of the propulsion system, generally speaking, an engine, a main propulsion engine, or possibly series of engines. So that's really the first and really main level of the validation that we have now. We have some capacity because some ships are equipped with a bit more intricate sensors to actually measure fuel flow. So in that case, you can actually go to, I guess you could say, a bit more, a bit better validation, really, of what is in near real time, right? On a second by second basis, how is the engine operation changing? How much fuel is it consuming at any particular wind condition at any point along the journey? And so I mean, the short answer is, of course, the more real world data you have, ultimately the higher the fidelity of the final numerical tool. If you have very, very little real world data to work with, then you only have so many areas, right, where you can really ensure that your numerical tool is matching the performance of the real world physical asset, versus when you have more information, you have a better opportunity, really, to improve that model.
How quickly are you able to, within the project, how quickly are you able to take the data off of the ship, look at it ashore as the project team, and then try and put that back into the ship to sort of make some sort of validated assumptions about that data?
Yeah, at this point, I would say from the time that the data from the sea trials is delivered, because again, the tool already exists, if applying it is just a matter of really a day or so of simulation, and then perhaps a few more days of thinking about it a bit more closely. But that process can in principle happen very quickly. We get the results from a sea trial and we can make some interesting conclusion about it quite quickly. And then of course you want to have a little bit more involved thinking process about the data and what it means, so you can draw, say, more general conclusions and get a better idea of how to improve ship performance. But at least just raw conclusions can come quite quickly. Yeah. The reason I was thinking that was because a ship sailing will have different, going back to the environmental conditions we were talking about, wind and wave will have different conditions. If it's too long, obviously you won't be able to replicate those environmental conditions very well to sort of match a shift in how you've aligned the wind propulsion system or the engine power, for example. Sort of if you got so many variables, I'm just curious into if you've got so many variables like that wind, when you come back with a suggested change, to see how that affects the vessel performance, how you remove those uncertainties. Removing uncertainties is, as with all, it's difficult at a laboratory scale to not necessarily remove uncertainty, but to account for uncertainty. And at an industrial scale, it's even more difficult, but not impossible. And that starts with, of course, identifying the sources of uncertainty. So from the beginning, this is we have this measurement, okay, yes, but in fact, what's the margin of error for this measurement, and then again, what does that mean for the validation of the model, whether it fits within that envelope, which of course also says that in some cases, if there's a sensor that perhaps just has a problem, then you identify, well, there's just actually too much uncertainty in this measurement for it to be useful for the validation of a model. Because again, the range of answers that you can get from a very uncertain experimental measurement is just too great to draw a conclusion, because you can see a trend in the solution that you get, but if the uncertainty is so large, then the trend can just be completely washed out. So that's really a very important aspect of this whole process. And the sea trials that were conducted as part of the WASP project, they've been relatively short sea trials for exactly this reason, that we wanted to get rid of sort of changes in wind direction and wind speed. So it was a matter of, I don't know, maybe a quarter of an hour or so each leg on those sea trials, and then you basically collect data for one point, and you know what the conditions are, and then you know what the fuel consumption was, or say the main engine power setting, and what the ship speed was. So that's one part of the puzzle, and then you let your simulation model loose and try to predict it, and then you can just compare power consumption or ship speed or whatever comes out of your model. So that's one way to do it. In full scale trials, you see this basin behind me. That's another way, not part of the WASP project, but you could obviously all do this experimentally also. You can test it in a wave basin like this. I've got a question from Neil Richards. Neil, if you want to ask this question yourself, you're more than welcome to, or I can read it out for you.
But he's asking, I'm going to try and read it out fully here. Given an instrumented wind assist unit or units, how is this output data, local apparent wind stresses, etc., integrated with the ship data, propulsion revolutions, fuel consumption, etc.? Would the wind unit data be sent separately to the digital twin cloud via a dedicated data connection, or combined and sent by, say, the ship's existing Inmarsat connection? What sort of data bandwidth requirements might be expected? Is there a perceived need for some edge processing to reprocess some of the raw data to keep bandwidth costs as low as possible? And presumably both the ship data and the wind unit data would need to be stored on a database in the cloud, and some sort of API provided for post-processing and UX functions. Can you share how this is architected for the WASP project? Joshua, data off the ship, data on the ship, edge processing on board the ship in any way? And what sort of architecture have you built up around this data?
No, that's a very excellent question. I I unfortunately have to give a somewhat maybe disappointing response, but I can say something not as disappointing. So in the context of the WASP project, these retrofit solutions, there's not a direct integration between the wind propulsion unit and the rest of the ship and the rest of the propulsion system of the ship. So the wind unit, yes, it has its own sensors, so it knows, again, how to adjust itself given changing wind conditions for optimal thrust and minimizing drag. But there's no direct integration with the main propulsion engine or propeller of this ship. So in actual fact, it's a challenge for these sea trials, because it's a part of our challenge in going forward with developing best practices and being able to do apples to apples comparisons of wind to no wind. Because of course, when you have the wind propulsion unit deployed, the speed of the ship changes, and it's very difficult to keep a constant ship speed, obviously, without having that full integration of the propulsion system. So that's the disappointing response, that in the context of WASP, there is no architecture for that. But of course, going forwards, it will be absolutely necessary, because we will have to have an automated control system. Now, how involved that control system is, it really depends on what I would say is, similar to an automotive context, it's the degree of hybridization. So if you have a ship that has conditions where the wind propulsion unit is starting to provide quite a significant part of the propulsive thrust, 20, 30, 40%, where really then the rest of your propulsion system has to operate quite a bit more dynamically. It's not just going at some steady state condition. The integration of the two systems, the wind and the engine main propulsion system, is essential. Otherwise, you essentially will just go much faster on the ship, which says, okay, you can arrive in a faster time, but the fuel that you're burning, you're doing it, and you're essentially doing it in a less efficient manner by having increased resistance on the hull, for instance. And these are things, having elaborate control of the ship, requires a full integration, a full hybrid propulsion system, basically. But exactly what that is, that's not something that's a goal of this project. But storing the data in the cloud, of course, I think, especially in the early days, when we get to the point of a strong or full wind hybrid propulsion system, that data is going to be invaluable. So of course, it's something that we would certainly store in a database to be able to reference.
Frederik, have you got any thoughts on that question?
Well, yeah, I agree. I mean, this is early days. We're trying to develop something here, and it is like it is at the moment. There is no real-time connection to the ship. It's the data at the moment. The data comes off the WASP ships on the laptop of my colleagues. So this the stage where we're at. But I mean, data connection obviously it's an important question in the end. But at the moment, we're trying to kind of get the base models and the concepts behind this going.
Maybe there's a few people on the call today that come from technology companies. Maybe I can kind of encourage them to make comments here about how they see the data flows related to the systems and the shore side, or even the edge side of things. When we talk about edge, I'm presuming we're meaning the automated system and the computing system on board the vessel that would respond to the environmental and the engine performance conditions to find that balance. There may be somebody who could give some insight into that. But let me go back to one of Giovanni's questions here, Josh, just going back and to what you were saying and what Frederik was saying in terms of the real world ship data being publicly available. I'm guessing the manufacturers of the systems may have some caveats to what can be made publicly available, but what can you tell me about how this work from the WASP project is going to create more awareness about the use? I mean, in this context, not awareness per se about wind assist solutions. I know that's the overarching project goal, one of the overarching project goals of the WASP project, but I'm thinking here about the data side of things, the digital twin and the data. What, in terms of what we're talking about here in terms of digital twins, do you see being publicly available?
Yeah, well, you know, the raw results, if you want to call it that, so logged data, things like that are of course going to stay within the consortium. But that being said, there really will be quite some results that will be publicized. There is already a few, even the example that I use in my slides, that's about to be public. That's a work my PhD student did that's going to be presented at the Oceans Conference tomorrow, in fact. So that's publicly available. And as we evolve further, of course, we'll have more real world results from the digital twins. It's mostly been numerical to this point as we start to apply the results of the sea trials. And much of that will be available in the form of publications, but also other events through the WASP project where we really showcase and really have a presentation of some of the high level results, you know, the fuel that's saved, the CO2 that's avoided. These are direct deliverables of the project. So of course, those will be publicized. That goes without saying.
Frederik, when it comes to digital twins per se, and I mean on the broader picture of what a digital twin is there a need for standardization around this, or do we see the large technology companies, the digital companies, the class societies that are pushing the digital twin envelope here, are they developing their own definitions of digital twins? Or is there a need to look at a common approach to digital twins that fits everything to a point? Because I know in one of your first slides, you showed how digital twin can be applied in architecture, it can be applied in automobile industry, etc. So can you comment a little bit about the differences, the different twins, if you like?
Well, in my mind, this will always be specific. Either be it to the sort of company or the technology used, or well, it might even be ship specific. Maybe not the sort of general approach, and the standardization would of course be nice. Yeah,
is there need for standardization?
In the long run, I would say yes. And from my perspective, that's not the main problem right now, because it's, as I said, it's early days. We need to get the sort of basic ideas right, and need to get the simulation layers behind this right. And then once we start assembling layers, a sort of common architecture, of course, helps to make it easier.
Yeah. we've got another 20 odd minutes, and I still see that there is about 26 people still on this call. Nobody else seems to want to have a question. I guess I'm thoroughly entertaining you by talking to Frederik and Josh here and answering all of your questions, maybe. But if you do want to raise your hand and ask a question or make a comment, if anybody comes from one of the technology companies, maybe you've got some thoughts here about how digitalization and wind can be applied together in this digital twin context, or maybe somebody from academia has got some additional research they want to highlight and talk about, because this is a very good element where we see academia and technology and business working together to push the envelope here and to push things forward. So it'll be good to hear from you all and get your thoughts on this kind of project, on these kind of solutions, to see how you're moving forward with that. Otherwise, I will continue just drinking my cup of tea and having a chat with Josh and Frederik and asking the questions. Gavin, all right, are you going to raise your hand?
Yes, I've just raised my little orange hand as well, which is found the button. Yes, I was just wondering about the differences between the digital twin that is being used in this project and, say, a digital twin that would be developed for, I don't know, for a hydrogen propulsion system or for other aspects of the decarbonization process. Are we talking about a very similar process, or are there some sort of fundamental differences there?
I guess that's to Frederik.
No, I think the fundamental approach is quite likely to be similar. It's the equations that Josh showed, and then it's sort of this equation. It was basically a force balance. So then the individual forces that you're balancing, they depend on the ship and the propulsion system and so on. So there might be smaller differences, but it's quite likely that it will be a very, very similar approach, and you sort of start changing out little building blocks of this model, but not the sort of overall approach.
Would it also allow you to see where things are missing, Frederik? Because I'm just looking at the diagram that Josh showed, where you've got the sort of the basic model of the basic building blocks. But if you put everything into equation and you don't get out the result, then are you indicating, is it a way to identify where some factor may be missing, some force may be missing? So, I mean, I know this isn't the case, but let's say you weren't accounting for wave height and you looked at your data and you couldn't make the digital picture and the real picture match, you would then look for something missing. You knew to look for something. Is this an opportunity in the development of solutions to look for what's missing, for what data you need to continue to make improvements?
Yes, and I mean, to be honest, of course, there's something missing, and we've done those seed trials in the WASP project, and we figured out that interaction between multiple propulsive devices, between sails and the hull, is probably a much bigger issue than we expected initially. So if you stick two sails on a ship, you cannot just say propulsive force is 2 times sail force at this particular angle and wind speed. There's stuff going on which we still don't fully understand, or well, we understand it, but there's still ongoing research how to model this, and this is the big advantage of having such sea trials or experiments, that you can sort of validate your models and see how good they are.
Joshua.
Yeah, I mean, I would agree with some of those comments. It again, having the access to the real world data you feed that back into your model, you try to validate, and then you can become immediately aware if there is some discrepancy between the two. Then of course you try to determine, why is the discrepancy there? Is there some effect that I'm not capturing, that I'm not able to explain, and iterate, and it allows you to improve the model and hopefully the understanding of the physical process and of the physical asset and why. I mean, yeah, if it's interaction of between sails and how that impacts the wind that one sail sees versus another, which of course is a very complicated effect. And that's something that's very difficult to account for, especially now, yeah, in sort of these early days. But we will get there.
And can you give any sort of flavor to that in terms of how you see that with the different types of systems that you've got within the WASP project? Because obviously you haven't got one technology, you've got a few different technologies. How are you seeing that across the different technology solutions?
In terms of just if there's yeah, certain discrepancies between the real world and the model. Yeah, well, so I mean, one of the ships in particular just has a single Flettner rotor on it, so but even that, it's still, at least initially, somewhat difficult to characterize the performance of that rotor because of this, the effect of the wind coming over the hull of the ship, and exactly what wind does the wind propulsion unit see. And in fact, it sees different wind depending on the height that you are from the surface of the ocean, because there's a boundary layer, right, between the ocean surface and the sort of free stream velocity of the wind, which isn't impacted by any sort of surface. I would say that, I mean, that's been probably common across all of the technologies. And so we, of course, have to make some simplifying assumptions about, all right, well, where do we consider, where do we consider, where's our measurement of wind on the unit, because these units of course have finite heights or lengths, if you want to say that way. And that's actually a very important part of this process. Is we have to make simplifying assumptions to be able to do this analysis, but obviously we can't go too simple for fear of actually not capturing some effects. And that's something that we can see is if there's that discrepancy, it says something is too simple. The model is too simple, and there's just something that we need to add or better characterize.
Good, thank you. If anybody has got any other questions or comments, then Neil, we actually see you and hear you now. Welcome.
Yeah, sorry, I'm on an iPad. That was the only way I was able to get a webcam set up. So, sorry, I just thought I'd offer some opinions. Not being an expert in this area related to big ships, but I did spend 2 years working on a digital twin system for a non-maritime related application, and thinking about this for wind assistance and for ships. My first thoughts are that there's probably 3 main areas where it's useful. One is the obvious operation and maintenance side of things, because if you can record the stresses on your wind unit, your wind propulsion system, or any data that's coming in, then obviously the designers and manufacturers of the wind unit are going to be able to get useful information. And also any signs of early failure and things like that. So there's a kind of a practical side of it which is useful to the designers and manufacturers. But as far as the ship owners and ship people are concerned, there's 2 levels to it. There's obviously the ship itself, and I think Joshua's point about moving to an integrated hybrid type of approach where the control system is locally integrated to take advantage of the wind much more closely is an obvious one, and it seems like a very interesting area to explore. I think that's a very rich area of investigation. But there's another one for the owners and operators, I think, which is that you've got real-time data from your ship. And it seems to me that this is going to be useful, not just sort of economically and practically, but possibly tied in with wind routing information and stuff like that. I see that a lot of people see that wind routing is going to be the sort of the key to taking the best advantage of this. And it seems to me that integrating real-time data from the ship is the key to tuning that and making use of it. As I say, no first-hand experience, but that's just my initial thoughts on the whole thing.
Good, thank you, Neil. Josh, I'm not sure if you wanted to comment on that. There wasn't a real question, but
yeah, no, I mean, I would just say one, because we haven't really said anything about it yet, about weather routing is very not something that we're directly addressing again in the WASP project, because we don't really have the full integration of an energy management or a control system of the ship. But yeah, going forwards, it is going to be quite an important issue. And again, it's also very difficult, even when you have a full characterization of the ship and you have characterization of weather conditions and wind conditions, it still becomes somewhat difficult to estimate fuel savings or to make suggestions, just because, yes, you can turn the ship and go somewhere to get some more favorable wind conditions. But of course, you also may increase the length or time of the route. But there's also other considerations of other vessels that actually prohibit you from making the optimal choice. So it's really in a control sense, it's a very, very challenging problem, but it is a very large space to explore. And I am sure it will be explored in very much detail in the future. I expect it.
I want to turn to a question that's come in from Cortland Jensen. Cortland, you're more than welcome to ask this question yourself if you like, but I'll start by reading it out. Is adaptability to different ships with, I assume, a variety of information available, as well as sensors installed, as well as the capabilities of different ship operators, of concern at this point? In other words, taking the data and applying it to other vessels, I think is what he means here, Josh. I imagine that the physical modeling, especially when using real data, would change based on the ship. Would there be options for physical modeling available for ships that lack certain real data, i.e. different simplifying assumptions? So Josh, I think I'd like you to tackle that.
Yeah, there's always a difficulty in a sort of a scientific sense of extrapolation versus interpolation, right? So interpolation says, okay, I understand some system and I simulate, or I try to make some prediction about a condition which is in my range of understanding or knowledge based on my validated model. Versus extrapolation, it's not to say you can't do it, but it always comes with some risk or caveat, which is, well, I'm going outside the bounds of what's validated. So then there's always the question of, well, the solution you get, how valid is it? And it's very hard for you to say as the modeler, because you haven't necessarily validated the model at those conditions outside the bounds. Now, it's not to say that such data can't be used, at least for rough estimations, maybe in kind of an initial design phase. But again, yeah, I would say it's just done with that caveat that of course you're extrapolating from the model, from the validated model that you have. And as long as you have that understanding, well, then you can use those results accordingly. I think that's what I would say.
Frederik, have you got any thoughts on that question?
Yes, I mean, the simple and the usual example here is maybe the ship resistance, and it depends on what sources of information you have available. So if we talk about physical modeling approaches, then yeah, this of course, this will vary from ship to ship, and you just need to find your best sort of source of information there, which might be CFD calculations or tank tests or whatever. But now we also have a ship in operation which collects data real time. So this sort of initial guess, your best guess that you've done based on, say, simulation, CFD simulations, you can sort of improve this over time and say, okay, under those conditions, the resistance seems to have been a bit lower, and then you sort of correct your resistance curve, and you start building up knowledge over time, kind of the machine learning approach there.
Yeah. And actually, that sort of machine learning we'll touch into. Gavin's just come back with a question, and it relates to what Neil was asking or the point he was making about maintenance and being predictive maintenance. And I realized that this is kind of not directly in the scope of the WASP project in terms of the performance data, but when it comes to predictive maintenance, machine learning and prediction of faults and such is an element that I know a number of the class societies have been working here. But can you comment, Frederik, about how in the context of wind assist propulsion or generally, how you see the digital twin being used in predictive maintenance of onboard technology, especially given that there is a large focus by OEMs on that as well?
In my mind, it's another, this maintenance prediction is another layer to your digital twin. So say if you're operating a rotor or suction sail, you will log hours on it. You will know how many RPMs you've already done over the last 10 years, and then you can make a prediction how long it's going to take you until you have to exchange, say, main bearings or whatever. So it's a question of logging data, storing it, and making it accessible.
And is there, when you talk about the layers, Frederik, do you see them almost being separate, or are they very well integrated with each other? Does one layer have an influence on the other layer? I realize there are different types of layers, as you pointed out, but I'm just wondering, I'm trying to sort of just get a picture. This is the thing about the digital twin. It all has to be very visual, doesn't it, for us humans? But I'm just trying to get that picture about, I'm just almost visualizing layers that are not necessarily integrated into each other. So how does data from one layer influence the decisions that are being made on another layer?
Well, as I picture it, it's different layers where each layer corresponds to a particular modeling approach. So you might have this famous force balance for performance prediction, and then just RPM counting for maintenance, and a few multiplications and the oil price for your economic module. And then all those layers, they send information to I would say a kind of interface or evaluation, and then you can draw a conclusion if you post-process layer from those three data. Is it better to go into dock now, or should I wait another half year and give it a few more revolutions before I start changing bearings? And you might, decide to do it now because the oil price is very high, so it's good to be in the dock instead of doing it later.
Yeah. Good. Thank you, Frederik and Josh. We're coming up to the last couple of minutes, and I don't think we have any more questions coming in. Nobody's waving their hand physically or digitally. So I'd like to thank everybody for their input here, and thank you, Josh and Frederik, and for NMT for hosting us. And Gavin, I think I'll hand over to you for your last words.
Okay, thank you, Craig, and thank you very much to Frederik and Josh for sharing their insights. I remember when this webinar was first proposed, and I really showed my ignorance around digital twins. That has been demystified for me very, very much during this webinar. So I thank both Frederik and Josh, and also Craig for leading the charge on drilling down into a lot more of that kind of granular detail. It's a really fascinating discussion. And of course, this will be recorded. This has been recorded and will be available publicly. And if you do want more information on these aspects, Josh and Frederik have both put their emails at the top of the chat. So please do avail yourself of that. Of course, check out the WASP project, and there's a lot of details there. The newsletter has just come out recently, and there's some speed trial aspects in there as well, which obviously will feed into the digital twin development going forward. We will have a couple more seminars coming up. Probably the next one will be around those technical results, and then that will be followed by sort of business cases and the financial cases of the applications and getting getting those onto ships. But without further ado, I'd like to say thank you very much once again to Dr. Frederik Gerhardt, Senior Technical Expert with SSPA, and Professor Josh Lacey from KU Leuven, Faculty of Engineering Technology. And once again, thank you to Craig from Fathom World for his excellent moderation. And thank you to all of you for joining us. And hopefully you're walking away with a far better idea of what the digital twins are and how they apply to wind propulsion technologies going forward. Thank you very much.
Thank you, everybody.
Well, thanks.
Enjoy the
Thanks,
day.
everyone.
It's been a
Bye.
pleasure. Bye.